So when we talk about whenever we talk about any heat energy change, okay? So we can understand any heat energy change by looking at a cooling curve or a heating curve. If I draw for you, let's say a heating curve, okay? You and I have with us, you and I have with us, let's say a block of ice, okay? That block of ice is at -4 degrees centigrade. You take it out of the freezer, you put it down in a pot of water, in a pot. Okay. You place that pot on the stove and you turn on the stove. So your graph will actually look something like this. Okay. This over here, where the temperature is at over here, the temperature is going to be at -4 degrees centigrade. Okay. Then this is 0 degrees centigrade, and this is basically when you observe melting. Or if you're doing the opposite, you're cooling it down, you will observe freezing. Then again, the temperature increases until you get to 100 degrees centigrade. And over here, you will observe either boiling if you are providing the heat, or if you're cooling it down, you will observe condensation. Now, we can understand this entire graph by taking a look at two particular scenarios. The two scenarios that we can go ahead and take a look at are the specific heat capacity and latent heat. So to understand let's start with first talking about our specific heat capacity. What exactly is specific heat capacity? Specific heat capacity is the energy required to increase the temperature of 1 unit mass by 1 degree of a substance. So the energy that we need to increase the temperature of 1 unit mass by 1 degrees of a substance is referred to as specific heat capacity, meaning that I have, for example, 1 kilogram of water. How much temperature or how much heat energy do I need to increase the temperature of 1 kg water by 1 degree Kelvin? That is specific heat capacity of water. Specific heat capacity of water. I have a block of aluminum. How much energy do I need to increase the temperature of 1 kg aluminum by 1 degrees? That is the specific heat capacity of aluminum. And if you have to calculate the specific heat capacity, this is the formula that we use. E is equals to mc delta T, where E stands for the energy required, which is measured in joules. M stands for mass, which is in kilograms. It can also be in grams. The unit will depend upon the value of C basically. C stands for specific heat capacity. The unit we have for this is generally joules per kilogram per degree centigrade, or you can also have it in Kelvin. That is also possible. Okay. And then, of course, we have delta T. Delta T is change in temperature. This change in temperature can either be in degree centigrade or Kelvin. Now, so this is your specific heat capacity. Specific heat capacity is going to be different for different substances. So every substance is going to have a different, every substance is going to have a different value. Okay. Now, if you if you go back to the graph that I have shown you, so if you go back to the graph that I've shown you, you are going to notice something very interesting. You're going to notice that there are certain areas of the graph where the line is completely horizontal. And you will notice that that happens specifically when there is a change in state. Okay. You will notice that when there is a change in state, there is no rise in temperature. Why is it that when there is a change in state, there is no rise in temperature? To understand that, we need to understand what is temperature. Temperature is basically the measure of average kinetic energy of the molecules or whatever particles are there, ions, positive ions, negative electrons, metallic bonding, doesn't matter. The average kinetic energy of the particles. So how does, for example, a thermometer work? The way a thermometer works is like this, that if I have a glass of water, inside the glass of water, I have my thermometer. Now, inside this glass of water, I will have water molecules. Those water molecules will have a certain amount of kinetic energy. Okay. So the molecules have a certain amount of kinetic energy. How much kinetic energy they have depends upon the heat energy. Okay. They have a certain kinetic energy. When they will collide with the thermometer, they will transfer the energy to the thermometer. That, for example, if I give you the example of the most common thermometer we use a mercury thermometer. So energy is transferred to the thermometer, and that energy causes the mercury to expand. And that is recorded as temperature. So that is what we say, that this is the temperature. This is how the system basically works. So now, if you heat up the water, the molecules will gain more kinetic energy, more collisions with the thermometer, more energy is transferred, so the mercury will expand more and you will record a higher temperature. Okay, so temperature is a direct measure of the kinetic energy of the molecules. The more kinetic energy the molecules have, the more temperature you are basically going to end up recording. Now, when we talk about go back to our graph. So in your graph, you will notice that whenever there is a change in state, there is no rise in temperature. Why is there no rise in temperature? Because all the heat energy is used in overcoming the bonds or forces of attraction between the particles. all energy is used to overcome the bonds between the particles, right? So there is no increase in kinetic energy. All of the heat energy that you are supplying is being used to overcome or break the bonds between the particles. So there is no energy being converted into kinetic energy of the molecules. As a result, what do we see? That whenever there is going to be a change in state, the temperature will not rise. Because there is no change in kinetic energy, no gain in kinetic energy, all the energy is being used in changing the state. All the energy is being used in overcoming the bonds of attraction or the forces of attraction between the particles. And this brings us to our latent heat. Just like we have specific heat, we can have latent heat. When you talk about latent heat, what is latent heat? Latent heat is energy required per unit mass to change the state of a substance. Just give me a second. Okay, so the energy required per unit mass to change the state of a substance. So if I have 1 gram of water, how much energy do I need to change its state, right? That is latent heat capacity. The formula of latent heat capacity is E is equals to ml. See, there is no delta T. Why? Because there is no rise in temperature. The only thing that's happening is the state is changing. So how much energy do I need for 1 kg substance? 1 kg water. That is the latent heat of water. How much do I need for 1 kg of aluminium? That is the latent heat of aluminium. So E, of course, stands for energy required in joules. Or this can also be in kilojoules, by the way. M stands for mass in kilograms. And L stands for latent heat capacity. And this is normally in joules per kilogram. Then when we talk about latent heat, so we can have two types of latent heat. Latent heat of fusion and latent heat of vaporization. Latent heat of fusion is when you go from solid to liquid or liquid to solid. Okay, so when you are melting it or when you are freezing it, that is latent heat of fusion. Then we have latent heat of vaporization, which is when you go from liquid to gas or gas to liquid. So, these are the two major terminologies or the two major definitions that you should know about. So, we can have latent heat of vaporization or we can have latent heat of fusion. Now, when we are talking about our topic of thermal physics, right? Remember how we went over our temperature. So let's take a look at the concept of temperature in a bit more detail. Especially, let's go ahead and talk about your different types of thermometers, the different properties of thermometers. Okay, that is what we have to go over, the different types of thermometers and the different properties of thermometers. And then we obviously have to talk about our temperature scale. So when we talk about our thermometers, let's go ahead and do that. There are different types of thermometers that are a part that you will encounter in your past paper or in your syllabus. So a few have obviously, Hajra, a few thermometers that we use normally. So we can have, for example, what is known as a liquid in glass thermometer. Liquid in glass thermometer, the examples that we can have of liquid in glass thermometer is obviously your mercury thermometer. The one, mercury thermometer is the one that's used really, really commonly in, especially in your medical aspect. Whenever you talk about, measuring your measuring the temperature of your, like, of any patient. So generally to check a fever and all that, we use mercury thermometer. So mercury thermometer is an example of liquid and glass thermometer. Then we can obviously have alcohol as well. Then water can also be used. So when you talk about your liquid in glass thermometer, right? So a liquid in glass thermometer generally has the basic concept that goes this way. You have a bulb, okay? That bulb actually has the liquid inside of it, okay? Well, excuse my really weird thermometer. Anyway, so the liquid is over here in the bulb, okay? Then on the main stem of the thermometer, you have your tube like this. And with the tube, you have your scale. So now over here, generally, like I was telling you, we can have our different types of thermometers. We can have mercury thermometers, alcohol thermometers, and you can also have water if you want. The principle will be the same. So when you are talking about calibration of a thermometer, okay, the calibration of a thermometer we can do with the help of water. Okay, so for example, if you place the thermometer in ice, you can record the expansion. So you place the thermometer in ice, and when you place the thermometer in ice, you will get your you will find out the 0 degree marking. So you mark on your scale that this is where 0 degree centigrade is. Then you can put it in boiling water. When you put it in boiling water, that will correspond to 100 degree centigrade. Now, the next part is that assuming that whatever material you are using, alcohol, mercury, it has a linear expansion. Okay. Assuming that whatever material is, it has a linear expansion. Linear expansion means that it will expand the same amount for each degree increase in temperature. So same expansion for each degree rise in temperature. So for example, if mercury expands 0.5 centimeter for 1 degrees, so it's the same throughout, right? It is going to keep on expanding by 0.5, 0.5, 0.5. That is linear expansion. Some substances give non-linear expansion. Non-linear expansion is, like from 0 to 10, it was increasing by 0.5. Then from 10 to 20, it started to increase by 1 centimeter, 1 centimeter, 1 centimeter, right? So it's not staying uniform, the expansion, it's changing. So that is non-linear. So if you have a linear expansion, then you can simply divide the scale into even units. So meaning that you have 0 degrees and 100 degrees centigrade, you just divide it into even points. That's it. And you will have your entire scale calibrated, and you will have your entire scale as ready. Okay, so you just divide it into equal units. So for example, you could divide it into 100 divisions, 100 units equally, right? So this is basically when you have a linear expansion. And when you talk about so ice is basically your lower fixed point, and boiling point of water is your upper fixed point. Then when we are talking about so this is what we can do. There are, to be very honest, depending upon the scale, we can have different fixed points. So for example, if I want a scale that is going all the way to 1,000 degrees, I can even use the freezing point of gold or freezing point of silver. Okay. So that will give me a really high temperature. So this is basically just we're using water if you want a small scale. But if you want a really large scale, you can even change up the values. Now, one of the things that you should know about your liquid and glass thermometers is the properties of thermometers. When you talk about the properties of thermometers, so the properties of thermometers, number one property that we have to understand is sensitivity. Sensitivity. I excuse my pronunciation. Sensitivity. Sensitivity is how do we define sensitivity? Sensitivity is how much the material expands per unit temperature rise. So, for example, if the temperature increases by 1 Kelvin, how much is the mercury going to expand, or how much is the liquid going to expand? If you have two thermometers, okay, in one thermometer for the same temperature rise, per degree temperature rise or same temperature rise. So if you have two, let's say, thermometers, okay, and in your two thermometers, one thermometer will expand, gives you a greater expansion, okay? The temperature that they're both recording is the same. The other one gives you a smaller expansion. So the one that gives you a larger expansion is more sensitive, right? Basically, depending upon the response, right? So if you get like a stronger response, that is more sensitive. So to increase the sensitivity, we can use a narrower tube. A narrower tube increases sensitivity. So the smaller your tube is going to be, the more sensitive your thermometer is going to be. Then the second property is range. Range is the upper and the lower, or the range is basically the the how low and how high the upper and the lower fixed point are. Okay, so when you talk about range, range is basically the basically uh less if you have a lower uh, 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 uh a range of values. I can't think of any other word to explain it other than range. But range of values is basically that you have two thermometers. One measures it from 0 degree centigrade to 100 degree centigrade. This is the range of thermometer number one. The thermometer number two measures, for example, from 40 degrees centigrade to 60 degrees centigrade. So you can clearly see the thermometer number one has a greater range because it measures a greater, it has the lower fixed point is less and the upper fixed point is higher. So it will measure a greater range of temperature or a greater value of temperature basically, right? Then when we talk about our number three, so the third property we have to talk about is responsiveness. Responsiveness is how quickly the material expands in response to change in temperature. Right? So, or temperature rise, or actually, I should not say temperature rise because temperature can decrease as well to change in temperature. Right? How quickly the material expands in change in response to any change in temperature. What that basically means is that the temperature has changed. So does the thermometer give you a result instantly, or does it take a little bit of time to give you the steady value? Right? That is the responsiveness. So the responsiveness depends upon the bulb, okay? The bulb of the thermometer. So this is the bulb of the thermometer. A bulb and or thicker glass. Okay, right? So if the bulb is large, that means there's a lot of, like if the bulb is large, it means there's a lot of liquid basically. So if the bulb is large, or you have the thermometer is made up of a thick glass. Okay, so that means that the thermometer will probably be less responsive. So if you want to make it more responsive, you should use a smaller bulb and use a thinner glass. Then the last property that we have is the last property we have already studied, that is linearity. Linearity means that the expansion should be a linear expansion. So some materials have linear expansion, some materials do not. There's nothing you can do about it. This is just a property of whatever liquid you're using. So these are the properties of the material and how you can actually change the properties of the thermometer. Now, there's another type of thermometer. So one type of thermometer is your liquid and glass thermometer. Another type of thermometer is a thermocouple. A thermocouple is um a thermocouple actually uses uh your electricity, okay, to actually figure out what the temperature change is going to be. So if we talk about our thermocouple, so our thermocouple actually looks like this. We generally take two different wires. So I'll draw them with two different colors to show that they should be of two different materials. So let's say that we have a wire over here that is made up of copper, and then we will have another wire over here that is, let's say, made up of iron. And in the middle, of course, we will need something to measure that electrical supply. So that will be a voltmeter. Then what you do is that this is copper, this is iron. So what happens that this one junction acts as the hot junction. The other junction acts as the cold junction. So for example, I have placed the cold junction in ice, and the hot junction I will place in my sample, whatever sample I'm trying to measure the temperature of. So there is going to be a difference in the temperature between ice and the sample to be measured, obviously, right? Now, this difference is going to, because temperature, as you remember from electricity, temperature affects the resistance of the material. So the change in temperature changes the resistance of the material. This will, so the temperature difference produces a difference in the voltage, and that gets recorded in the voltmeter. So if the greater the temperature difference is going to be, the higher your voltage is going to be. But so when we talk about the thermocouple, there are a few advantages and disadvantages of thermocouple. I'm going to share the list with you, a table with you actually that I have that will make it a bit easy. But when you talk about a thermocouple, one of the major disadvantages of a thermocouple is that it gives you non-linear results, right? The voltage change is non-linear, which means that maybe from 0 degrees to 10 degrees, it will give you 10 millivolts change. But then from 80 to 90, it might give you 100 millivolt change. So the change in voltage is not the same for change in temperature. So that changes. So that is one of the problems with the thermocouple. Mm. Okay, you know what? I think leave the temporal advantages and disadvantages. Hmm. Okay, I think don't bother with advantages and disadvantages, leave it. Okay, there is actually a third type of thermometer that you can use. And the third type of thermometer then you can use is a thermistor, because a thermistor also responds to rise in temperature, right? I'm not going to go over details of thermistor because you've studied thermistor very well before. But a thermistor also leads to rise in temperature. So you can also use a thermistor as a possible thermometer. So this was about the different type of thermometers that we can actually see. Making sense so far, Hajra? Any part that's not clear? Any part that's not making sense?
No.
Okay, great. All right. So for now, I think let's stop over here for today because I don't think we have the time to cover conduction, convection, radiation right now. So let's go ahead and um okay. Either it's up to you. If do you want to go ahead and take a look at one question, or do you want to? Okay, let's go ahead and take a look at one question. Give me a second. Hold on. Let's look at a question. Give me 1 second. All right. So our question says a student investigates the efficiency of the filament lamp. Figure 4.1 shows the filament lamp with its glass bulb immersed in water in a beaker. The reading on the thermometer in the water is 19 degrees centigrade. Only the glass of the lamp is in contact with the water and the electrical connections are completely insulated. The lamp is switched on. At the end of the experiment, the temperature of the water is 21.5. The mass of the water is 600 grams and specific heat capacity is 4200 joules per kilogram degree centigrade. So see, Hajra, the unit of specific heat capacity is very important in these questions. So if the unit was in grams, then you could have just used grams. But since they're using kilograms, you have to do the conversions. Show that the increase in internal energy is 6300 joules. So you have to basically calculate the energy. So go ahead, give this a try and just give me 1 second. I'm just grabbing a charger.
I got the answer is 6,300. So, Miss, Miss?
So sorry, Hajra, my device got completely stuck and it was lagging and it was not even restarting. So
Okay.
I've finally figured something out. I'm so sorry. Okay. Hajra, we'll do this question later. Later, we will go ahead and we'll start off with chemistry. Okay.
Okay.